tonight's journey drifts into one of the strangest solid places in the universe, the crust of a neutron star, a realm where matter locks into ultra-hard layers, where starquakes ripple through a shell only kilometers thick, and where nuclear pasta twists into sheets and ribbons under crushing gravity. In the next moments, the story moves from quiet texture to deep forces, from microscopic structure to a whole star settling into calm. If this kind of slow science makes the mind unwind, please, like the video, subscribe for more cosmic sleep documentaries and turn on notifications. Now let the darkness soften. Let the layers unfold. A neutron star crust looks like a thin shell, yet it behaves as one of the hardest forms of matter known. The crust is a rigid skin that locks in stress. It sets the surface shape and quietly steers how the star changes over time. In that region, the first sight is a curved plane of metal-like crystal that holds its pattern under gravity that leaves no room for softness. The surface carries minute ridges and shallow basins that follow the curve like ripples frozen into stone. Light behaves as if it skims polished rock, yet the rock is built from nuclei arranged in a tight grid. That grid is the first key. Matter chooses order because disorder cannot survive the pressure. A solid here is not a heap of grains. It is a repeating architecture that extends for long distances with defects that matter more than height. The main surprise arrives early. The crust can be about 1 kilometer thick, like the depth from a canyon rim to its floor. It still governs a sphere wider than many moons. At the other end of scale, lattice spacing is closer to a nucleus width than to a grain of sand. Between those extremes, a single shell connects the tiniest separations to a global curve. Thickness shrinks, influence grows. At the smallest scale, compression squeezes empty space out of atoms. Electrons flood the gaps and act like a dense, invisible sea that presses from every direction. The crust becomes a frozen foam. The bubbles are nuclei. The filler is electron pressure. A slow visual anchor settles in. Across the surface, a shallow trench runs for hundreds of kilometers. Its edges look crisp. Its floor sits slightly darker, as if a thin shadow rests in the dip. Nothing flows into it. The shape stays. That stillness unlocks the next idea. Shape means stored stress. When a solid keeps form under such weight, it also keeps a memory of strain for a long time. The crust is a reservoir for elastic energy. In ordinary rock, a crack relieves stress and ends the change. Stress can spread without obvious motion because the whole shell is locked into a global curve. Even a small bump matters. A ridge only as tall as a large tree would weigh like a mountain range under this gravity, yet the crust can hold it. The reason is simple in outline and strange in detail. Nuclei sit close enough that electric repulsion shapes the lattice. Electrons press back as a smooth background. This mix produces a solid that resists shear the sideways sliding that ordinary materials yield to. At a finer scale, the plane becomes a tiled field of repeating points. It resembles hoarfrost on cold stone. Each point is a nucleus. Tiles align into domains. Between domains, narrow seams appear where the pattern shifts by less than a step. These seams guide failure. Here a micro payoff lands. Starquakes do not require a thick layer. They require a stiff layer that can store strain and then release it. A signal would reveal that release is a sudden change in timing, because a rearrangement shifts how mass sits around the spin axis. Rotation stays smooth for long periods. Then a fault line slips and the smoothness jumps. Timescales widen. A quake can happen in a blink, yet the stress that feeds it can build for years or longer. Cooling plays a quiet role. Temperature gradients run from the warmer interior towards the colder surface. Those gradients change how easily the lattice yields. A warmer patch softens slightly. A cooler patch stiffens slightly. Small differences can decide where a fracture begins. Another payoff appears. Crust physics is not only about what exists, it is about where the same material is just close enough to failure. The surface trench remains as a calm reference point. Its shadowed floor is not merely a scar, it is a map of hidden stress written in curvature and reflected light. At this point, intuition meets a limit. At such densities, atoms are not neat spheres with empty space between them. Electrons do not orbit in tidy paths. They behave as a collective fluid. Nuclei are not isolated either. They interact through long-range electric forces and through the pressure of the electron sea. Models can describe this, but only indirectly. No direct image of the lattice exists. A signal that leaves the star is filtered by extreme gravity and by a thin outer layer, so only a narrow imprint reaches far distances. Even timing changes can be ambiguous because different internal arrangements can produce similar outward patterns. This is the limit of observation. The crust is inferred, not photographed. The limit sharpens what must be asked next. What conditions build the shell? What conditions break it? Deeper down, another layer enters without rushing. Pressure rises and nuclei become more neutron-rich. Neutrons begin to seep out and occupy the spaces between nuclei. A free neutron is a neutron not bound inside a nucleus. Like mist between rocks, free neutrons fill gaps without forming a visible surface. Like oil in sand, they change how the mixture responds when it is pushed. This matters because it nudges the crust from a simple crystal toward a composite part solid and part flowing component. The composite can still be stiff. It can also allow sudden slips when pin structures let go. Here another micro-payoff settles. The seeds of a starquake can lie in the tension between a rigid lattice and particles that would rather move through it. Now scale shifts outward again from the buried boundary to the whole star. The crust behaves like a dome. In a dome, a small distortion can redistribute tension across a wide span without any visible collapse. In the same way, stress paths run through the curved shell and return elsewhere as constraints. If the dome is stiff enough, it can ring in slow modes after a slip. If it is loaded enough, it can crack along its seams. The next section moves toward how this shell forms in the first place as a matter is crushed into order and then cooled into strength. A crust begins as a glow fades into a shell. The crust forms when pressure and cooling force matter into a crystal order. In that region, the first change is not a crack or a quake. It is the moment when motion loses freedom and becomes pattern. A young neutron star starts hot and bright beneath its own surface. Heat leaves the outer layers fast. Gravity keeps pressing. The outer skin becomes a place where temperature falls through a steep gradient. The gradient acts like a slow curtain. When the curtain passes a certain threshold, the liquid-like mixture stiffens. A visual anchor settles on a dim horizon. A thin sheen spreads across the curve like frost forming on a cold lake at dawn. The sheen is not water. It is nuclei beginning to lock into a repeating grid. The payoff arrives quietly. A solid is born not from dryness. It is born from order winning over agitation. The order has a source. Pressure squeezes nuclei close. Electrons fill the space between them as dense background. Electron pressure is the push from packed electrons. Like air in a sealed balloon, it presses back when squeezed. Here the air is invisible and far denser. This pressure supports the outer layers against collapse. It also encourages regular spacing. Nuclei settle into positions that reduce repulsion and fit the available volume. The result is a lattice. A lattice is a repeating arrangement of nuclei in a solid. Like tiles that lock into a floor, it carries force across wide areas. Like a honeycomb in stone, it spreads stress without moving much. This matters because it gives the crust a memory. A patterned solid can store strain without flowing away. Now scale shifts inward. The freezing begins at the smallest separations. It is decided by forces at nuclear distances. Then the effect spreads outward across a shell that curves around the whole star. The same event reaches from femtoscale spacing to a sphere many kilometers wide. One number can hold that shift. The crust becomes established within about a day, like a weather system settling after a storm. The exact moment varies with heat flow and composition. The order itself does not depend on clocks. It depends on the balance between heat and compression. Another visual anchor drifts into view. Beneath the sheen, faint bands appear. They curve like contour lines on a hillside. Each band marks a layer where density changes. The layers are thin compared with the star. They still matter. The payoff lands in the shape. Layers mean history. Each depth records a past state of pressure. As compression continues, nuclei change in small steps. Some electrons are pushed into nuclei. That process is called electron capture. Electron capture is an electron joining a nucleus and changing a proton. Like a seat swapping in a crowded row, a particle shifts identity. Like a key turning in a lock, charge changes without obvious motion. This matters because it alters which nuclei can exist at each depth. The crust becomes a stratified chemistry arranged by pressure. The physical details remain concrete. A boundary forms where one set of nuclei gives way to another. It is not a sharp wall like glass. It is a transition zone where the lattice spacing adjusts. In that zone, defects gather. Defects are small mismatches in the repeating pattern. Like a seam in cloth, they concentrate stress. Like a crease in paper, they guide where bending begins. This matters because future fractures prefer these seams. A limit of intuition arrives softly. At ordinary scales, freezing suggests a clear melting point in a clear liquid. Here, the mixture is not a simple melt. It is a plasma of nuclei and electrons under extreme gravity. The boundary between solid and liquid can be blurred. The best models rely on complex simulations. Those simulations depend on nuclear properties that are not fully known at such extremes. This is a limit of modelling. The crust is inferred from theory and indirect signals. The layer structure cannot be watched as it forms. It must be reconstructed from consequences. Another visual anchor steadies the scene. A smooth arc holds a faint mottled texture. The mottling looks like a field of pebbles pressed into varnish. Each pebble is not a stone. It is a nucleus locked in place. Between them, electrons act as a nearly uniform fluid. That fluid makes the solid conduct heat and electric currents. A payoff follows from that conduction. The crust is not only hard, it is a pathway. It carries heat outward and redistributes it along the shell. The pathway shapes how quickly the surface cools. It shapes which regions stiffen first. It shapes where stresses accumulate later. Now scale shifts again from formation to future. A young crust cools quickly at first. Then cooling slows over long ages. The early freeze sets the baseline. Later evolution modifies it. Thermal contraction can pull on the lattice. Magnetic forces can add shear. Accretion is absent in this world. No external debris is needed for a layered crust. Compression alone can create new layers as time passes. The microstructure matters. Grain boundaries and defects create a mosaic. Each domain can be aligned slightly differently. In a quiet sense, the crust resembles a field of basalt columns after lava cools. The columns are not the same. They still fit together. The primary analogy rests here. The crust is like basalt that cools into interlocking columns. It looks still. It hides stored tension in its joints. That matters because joints decide how a sudden slip travels. Another payoff appears in the joints. A quake does not need a giant ridge. It needs a weak seam in a strong shell. The early freeze determines where those seams start. The crust becomes a map of future fault lines. The final visual anchor returns to the layered curve. A faint ring of slightly different brightness circles the star. It comes from a band of different composition and conductivity. Light behaves as if the ring is polished differently. The ring is a subtle marker of depth and chemistry. The next section moves closer to the outer crust lattice itself. It lingers on how electrons and nuclei share the load in silence. A crust can look smooth from far away, yet up close it becomes a strict pattern of charge and spacing. The outer crust is a crystal of nuclei held apart by electric repulsion and supported by a dense sea of electrons. In that region, the primary visual anchor is a curved plane that looks like dark metal with an ultra-hard matte finish. The matte look comes from micro-roughness. The surface is stiff, yet it is not optically perfect. Countless tiny facets tilt by small angles. Light behaves as a scatter of faint glints rather than a single shine. The payoff is quiet and immediate. The same irregularity that dulls reflection can also mark where stress prefers to gather. The first core concept is the lattice. A lattice is a repeating pattern of nuclei in a solid. The pattern forms because nuclei repel each other. Gravity presses them close enough that regular spacing becomes the calm solution. Each nucleus sits in a pocket of electron charge. The pocket acts like a firm cushion. Like a tray of identical dimples, it gives each nucleus a stable place to rest. Like stones suspended in clear resin, the nuclei remain separated while the background stays continuous. This matters because repeating order allows force to travel through the shell without large motion. The second core concept is electron pressure. Electron pressure is the push from electrons packed into a small volume. When compression removes available states, resistance rises without needing heat. Like sand packed in a closed box, the contents push back on further squeeze. Like a stack of thin springs pressed together, stiffness grows as space disappears. This matters because the electron pressure supports the crust against collapse. It also sets how easily the lattice can be squeezed and how heat can move through it. One number can anchor the scale. In parts of the outer crust density can be about 1 billion tons in a teaspoon. That comparison is a guide for what hardness means here. At such density, empty space inside atoms is mostly gone. Distances shrink until electric forces dominate. A pinch of matter contains immense mass. The scale shift is gentle but complete. A structure decided at nucleus spacing shapes a shell that spans many kilometers in radius. Tiny separations decide global stiffness. A slow checkpoint crosses the matte plane. The surface shows faint polygonal patches that meet along thin lines. These lines are domain boundaries. Domain is the region where the lattice aligns in one direction. Where domains meet spacing mismatches form a seam. The seam can be only a few lattice steps wide. It can still guide stress. The payoff settles at once. Weakness does not require a hole. It can begin at a mismatch in alignment inside an otherwise strong crystal. The matter finish has another meaning. Microfacets scatter light and they also scatter vibrations in the lattice. Vibrations carry heat in a solid. When scattering rises, heat transport becomes less uniform. A physical detail appears as a temperature gradient that steepens near the surface. A thin layer cools faster than the material just below it. That creates a subtle contraction difference. The payoff arrives in the gradient, where cooling is uneven stress, can be added without any visible motion. The outer crust is not a perfectly uniform crystal. Composition changes with depth and with place. Some regions contain nuclei with slightly different charge. These differences interrupt perfect repetition. They create local strain. They also scatter vibrations and heat. Brightness reflects that complexity. A dimmer patch sits beside a brighter patch along the same arc. The dimmer patch reflects less because its microfacets point in a wider spread of directions. The brighter patch reflects more because its facets share a closer alignment. The payoff is carried by contrast. Optical dullness can trace mechanical complexity because both arise from small disorder. At this point, a limit of observation arrives softly. No direct view exists of the lattice itself. The repeating pattern lies far below any wavelength of light. The properties must be inferred from cooling behavior and from sudden changes in rotation. Even those clues are filtered by the outermost layers. Models rely on nuclear inputs at extreme density. Small uncertainties in those inputs can change predicted stiffness. This is the limit of modeling. Several different microstructures can produce similar large-scale signals. The crust is reconstructed from effects, not from images. Another visual anchor steadies the pace. Along the plane, a narrow ridge rises and then fades. It is sharp-edged like a crease in fired ceramic. A thin shadow clings to its leeward side. The shadow line tracks the curve and then vanishes over the horizon. The ridge matters because it stores stress. Under intense gravity, even a small ridge implies great pressure at its base. The crust can hold that pressure because the lattice distributes load through many connected bonds. A micro payoff follows the ridge. Hardness here is not only resistance to indentation, it is resistance to shear. Shear is sideways deformation without volume change. When shear builds, the lattice first flexes elastically. It then fails along seams. Domain boundaries and impurity zones become likely paths. This clarifies why starquakes can be sudden. Stress can build quietly across wide areas. Failure can then run along pre-existing seams in a short time. The electron sea adds a final twist. Electrons make the crust conductive and they link distant regions through shared pressure support. A local compression raises electron pressure and nudges neighbouring regions. The effect is not a flow, it is a shared stiffness. The primary analogy rests here. The crust resembles a thin sheet of glass under a gentle bend. The sheet looks still, yet tension spreads far from the point of load. In the same way, the outer crust can carry stress across a wide span without visible drift. The final checkpoint widens the view. The matte plane and its seams are only the outermost expression. With increasing depth, nuclei become more neutron-rich and spacing tightens. Eventually, neutrons begin to escape nuclei and occupy the gaps. That threshold changes the meaning of a seam and the meaning of stiffness. The next section moves downward towards that transition. It follows the crust into a layer where bound nuclei and free neutrons begin to share the same space. The crust changes character at a depth where particles begin to slip through the spaces that once seemed sealed. The inner crust begins when free neutrons appear between nuclei and form a hidden layer. In that region, the primary visual anchor is a slow snowfall of pale specks drifting through a dark lattice forest. The specks are not dust. They are neutrons moving in the gaps, silent and uncharged. The forest is the lattice of nuclei tall in the sense of repeating columns and pockets. A boundary separates the outer crust from this new mixture. The boundary is not a sharp line. It is a transition zone where nuclei become so neutron-rich that they cannot hold all neutrons. The physical detail is a layered gradient. Density rises with depth. Composition shifts with it. The payoff arrives early. The crust stops being only a solid grid. It becomes a composite, part locked and part quietly mobile. The first core concept is free neutrons. A free neutron is a neutron not bound inside a nucleus. One sentence holds the definition. 2 images return it to plain language. Like mist that fills the space between rocks, free neutrons occupy gaps without forming a surface. Like oil between grains, they can move through tight spaces while the grains stay put. This matters because motion can exist inside a solid without breaking its overall shape. The second core concept is the neutron drip transition. Neutron drip is the point where neutrons escape nuclei under pressure. It is not a drip like liquid, it is a threshold where binding energy loses against compression. Like a sponge squeezed until water appears between fibers, the nucleus can no longer keep all of its content. Like a crowded room that opens a side door, particles begin to occupy the hallway between clusters. This matters because it changes how stress and heat travel through the crust. Now, one number can anchor cell scale safely. The neutron drip transition occurs at roughly 400 trillion grams per cubic centimeter, like squeezing the mass of a mountain into a cup. The exact figure depends on the model. The order of magnitude is the stable guide. Scale shift follows naturally. At the micro scale, the change is a few neutrons leaving a nucleus. At the macro scale, an entire shell layer gains a new component that can flow through it. The crust now contains a hidden internal motion, even when the surface looks still. A visual checkpoint lingers on the lattice forest. Nuclei sit in pockets that repeat. Their charge keeps them separated. Between them, free neutrons form a faint background. They are uncharged, so they do not feel the same electric fences. They pass through the maze in a way that seems almost effortless. The payoff settles in a simple answer. This is why the inner crust can respond differently to stress than the outer crust. A rigid lattice can store shear. A mobile neutron background can relieve some stress or rearrange load paths without visible cracking. The inner crust is not softer in the ordinary sense. It is more complex. The composite can be strong and it can also host slippage at internal scales. Heat and vibrations move through this region with new scattering paths. Vibrations in the lattice can couple to the neutron background. Energy can be shared between the two components. Another visual anchor appears along the curved layers. A thin band glows a shade warmer than the layer above. The band is shallow, yet it stretches around the star like a faint ring. The ring marks a depth where composition changes quickly. That change can alter thermal conductivity. The payoff arrives with the ring. A small change in microphysics can create a large-scale pattern in temperature. Temperature patterns can then influence where stress builds over time. Now a limit of intuition arrives gently. At ordinary densities, a particle moving through a solid suggests a liquid channel or a crack. Here, free neutrons move without either. Their motion is quantum in nature and tied to dense matter physics. Direct observation is impossible. No signal can carry a picture of neutrons threading through nuclei. Inference relies on models of cooling and on timing changes of rotation. Those signals are filtered by the surface layers and by gravity. This is the limit of observation. Many internal arrangements can produce similar outward behavior. It is also a limit of modeling. The nuclear forces at these densities are uncertain. Small changes in assumed interactions can shift predicted boundaries and transport. The inner crust remains a place known through consequences, not through direct inspection. The story returns to physical texture. The lattice forest is not perfectly regular. It contains defects and domain boundaries. These features still exist here. The neutron background can smooth some stress, yet it can also concentrate other kinds. A domain boundary can act like a narrow channel where neutrons prefer to gather. Gathering changes local pressure. Pressure changes local lattice spacing. That can create a feedback where a seam becomes more distinct over time. The payoff is subtle and calm. The same region that helps relieve stress can also guide where stress returns. Composite matter can share load and still develop preferred pathways for change. The primary analogy rests here and remains unique. The inner crust is like a loaf of bread with a firm crust and a soft crumb beneath. The firm part holds shape. The crumb contains countless tiny pores where air can move. The pores do not collapse the loaf. They change how pressure is absorbed and how heat spreads. In the same way the lattice holds form while free neutrons occupy the pores of space between nuclei. Scale shift expands again from pores to sphere. This composite layer wraps the star like a hidden middle skin. It links the outer crystal to the deeper regions where nuclei distort further. As depth increases, pockets elongate. Shapes begin to stretch. Boundaries between clusters can become less like points and more like threads. That prepares the next step. The next section moves toward the strange geometries near the base of the crust. It follows how nuclei deform into pasta-like structures as density rises. Deep in the crust, geometry begins to replace the idea of separate round nuclei. Nuclear pasta appears when competing forces stretch nuclei into rods and sheets. In that region, the primary visual anchor is a layered canyon of glowing slabs that slide past each other in slow silence. The slabs are not rock. They are dense nuclear matter shaped into broad planes. Between planes, free neutrons form a thin mist. The mist is dark and featureless, yet it changes how the planes interact. The physical detail is a repeating pattern of layers with sharp edges. Each edge casts a narrow shadow into the gap. Light behaves as faint bands across the layers. The payoff arrives early. The crust near its base is not a simple crystal. It becomes a structured material with built-in channels and boundaries. The first core concept is nuclear pasta. Nuclear pasta is nuclear matter shaped into rods and sheets. The definition is brief and calm. 2 images return it to ordinary language. Like dough pressed through a grid, matter takes on long strands and broad sheets. Like stacked paper that has been compressed, layers form with thin separations. This matters because shape changes stiffness and changes how the crust can break. The second core concept is frustration. Frustration is competing forces that cannot both be satisfied. Here, electric repulsion wants nuclei to stay apart. The strong nuclear force wants nearby nucleons to clump. Gravity drives density higher. The result is compromised shapes. Round clusters become elongated. Elongated clusters merge into planes. The payoff follows from the compromise. Pasta is not an extra ingredient. It is the natural geometry of matter when two kinds of attraction and repulsion wrestle under extreme compression. One number can anchor the scale. The pasta layer can be about 100 meters thick, like the height of a tall city tower. Within that thin band, microshapes can steer global behavior. That is the scale shift. A change in geometry at length smaller than a grain of dust can affect a shell that wraps a star. The layered canyon returns as a slow checkpoint. Slabs curve gently. Some tilt, some merge. Their edges are not smooth. They have ripples that look like scallops carved into stone. The ripples create pockets where neutrons gather. The pockets slightly change local pressure. Pressure slightly changes spacing. A micro payoff lands. Even in this exotic region, the crust keeps a familiar rule. Small irregularities can seed large consequences because the whole structure is under constant load. Another visual anchor appears within the canyon. A thin filament runs between two slabs. The filament is a rod-like region of dense matter. It joins planes like a bridge. The bridge is narrow compared with the spacing between planes. It still matters. The payoff arrives in the bridge. Pasta can create connections that share stress across layers. That can make the material tougher in one direction and weaker in another. The pasta is anisotropic. Anisotropic means strength depends on direction. Like wood grain that splits more easily along one axis, pasta can guide fracture. Like layered shale that slides along bedding planes, sheets can shear along their interfaces. This matters because starquakes may prefer certain directions and shapes of rupture near the base of the crust. Now the story moves from static shape to slow motion. Free neutrons flow through gaps. They can carry momentum and energy. Their presence can lubricate some shear while locking other parts through pressure coupling. A slow payoff clarifies this. The pasta layer can both resist and redirect strain. It behaves like a mechanical filter. Some stresses are absorbed by bending of sheets. Some are passed upward toward the more crystalline layers above. Another checkpoint widens the view. The pasta layer lies near the boundary to the core. Above it, the inner crust contains lattice clusters and free neutrons. Below it, matter becomes more uniform. The boundary is a change in topology. Topology here means the connectivity of dense regions. Separate clusters connect into networks. Networks flatten into planes. Planes dissolve into a continuous medium. The physical detail is a gradient of connectivity. Small tunnels close, thin gaps narrow, sheets thicken. The payoff arrives at the gradient. The path from crust to core is not a single switch. It is a gradual rearrangement of shapes that changes how the star stores stress and how it cools. A limit of intuition arrives softly. Pasta is described by names that sound familiar, yet the shapes are not literal foods. They are patterns predicted by dense matter calculations. Direct observation is impossible. No surface signal can carry an image of rods and slabs. Inference relies on models of oscillations, cooling, and sudden timing changes. Those models depend on nuclear physics at extreme density. Uncertainties in the strong force at these conditions can change which shapes appear and how thick the pasta layer is. This is the limit of modelling. Several different microgeometries can produce similar large-scale stiffness. The star can hide its pasta in silence. The canyon scene steadies again. Sheets shift slightly as stress accumulates. The shift is slow at first, then it can become abrupt at a threshold. A shear plane can form along a layer interface. The interface is a boundary with low resistance in one direction. The payoff is immediate. This is a route for starquakes that begin deep and propagate upward. A fracture can start where sheets prefer to slide. It can then trigger failure in more brittle regions above. The primary analogy rests here and remains unique. The pasta layer resembles laminated pastry under a gentle bend. The layers hold shape when pressed from above. They still allow sliding along thin seams when stress becomes too large. This matters because layered materials can fail in a controlled way rather than in a single shattering break. A final scale shift softens the perspective. The pasta geometry is decided by forces at nuclear distances. Its consequences can shape global oscillations and timing changes that persist for years. The layered canyon fades into a broader shell. The next section moves from geometry to fracture. It follows how stress builds in a stiff crust and releases as a starquake with the pasta layer, acting as a deep hinge rather than a simple wall. A starquake begins as a quiet mismatch between what the crust wants and what gravity demands. A starquake is the sudden release of stored strain when the crust can no longer hold its shape. At this distance, the primary visual anchor is a hairline fault that curves around the star like a dark thread. The thread is not deep. It is thin and sharp, casts a narrow shadow along one edge, where the surface dips by a small amount. The surface remains matte and still, yet the fault line carries tension like a taut seam. The first payoff arrives early. A quake does not require a dramatic mountain. It requires a stiff shell that can store stress for a long time. The first core concept is elastic strain. Elastic strain is stored deformation that can be released. In ordinary solids, it is the bend held in a spring. Here it is held in a crystal shell. Like a bowed reed that stays curved until released, the crust keeps a hidden bend. Like a stretched drum skin that holds tension without moving, the shell stores energy in its tightness. This matters because stress can build with no visible change. The second core concept is yield. Yield is the point where a solid stops springing back. The crust can flex elastically. It can also fail. Failure can be a crack, a slip, or a rapid rearrangement along a seam. The physical details are clear. Seams exist at domain boundaries. They exist at impurity bands. They exist at layer interfaces near the pasta region. Along these seams, the lattice is slightly misaligned. The misalignment concentrates shear. Shear is sideways distortion. It grows when the shell is twisted or compressed unevenly. The story takes one number to anchor time. Stress can accumulate over about a year, like seasons passing without a visible storm. The exact span varies across objects and conditions. The scale shift follows. A slow build-up across as months or longer can end in a change that happens in less than a second. A long quiet tension can end in a brief slip. The fault thread returns as a calm checkpoint. Along the thread, a faint change in texture appears. On one side, microfacets tilt in one direction. On the other, they tilt in another. The boundary is visible as a subtle change in how light scatters. Light behaves as a slightly brighter band on one side. The band is a map of stress. The payoff is immediate. The crust can reveal its strain through tiny differences in surface scattering, even without cracks that open wide. Deep below the cores can come from several sources. Cooling shrinks the crust. Shrinkage pulls. Magnetic forces can add shear without touching the surface. Layered structure can encourage sliding along interfaces. The pasta region can act like a hinge. It can redirect stress upward. The quake begins where resistance is lowest. Resistance is lowest where seams and layers align with the stress direction. The primary analogy rests here and remains unique. The crust is like a ceramic glaze on a cooling pot. The glaze is strong and rigid. The pot beneath contracts at a slightly different rate. Fine cracks can form in a network when the mismatch becomes too large. The cracks appear suddenly. The mismatch builds slowly. This matters because starquakes are driven by mismatches between layers and forces, not by one dramatic push. Another visual anchor slows the pace. A long arc of the surface shows a faint ripple. The ripple is not a wave of liquid. It is a shallow change in height that propagates as a stress adjustment. It travels around the star. It does not need a moving medium. It is a redistribution of tension in a curved shell. The payoff follows the ripple. A quake can change the star's rotation because mass shifts inward or outward by a tiny amount. Even a tiny shift can alter timing. Timing's the cleanest clue that a quake has occurred. Now a limit of observation arrives gently and clearly. The fault thread itself cannot be seen from far away. The signals that reach distant space are indirect. They can be changes in rotation. They can be brief bursts of high-energy radiation in some cases. They can be changes in oscillation patterns. These signals do not uniquely identify the fracture path. Several different internal slip patterns can produce similar timing changes. This is the limit of inference. The crust's interior failure geometry cannot be reconstructed with high resolution. Models fill in the missing detail, but models depend on uncertain strength and composition profiles. This is the limit of modelling. The quake remains a best-fit story, not a filmed event. The narrative returns to mechanics with a calm checkpoint. Once a seam yields stress can transfer to neighbouring seams. The crack does not need to open wide. A slip of microscopic distance along a long interface can release large stored strain. The surface can shift by a small amount and still matter. Physical detail appears as a step in the terrain. One side of the fault sits slightly lower. A thin shadow lengthens along the step edge. The step is shallow, yet it extends far along the curve. The payoff settles with the step. In a strong crust, small displacements can correspond to large energies because the stressed volume is vast. Scale shifts outward again. A local slip in a narrow band can adjust the stress of an entire hemisphere. It can also excite global vibrations. Those vibrations can travel through the crust and reflect from the core boundary. Over time they fade. The surface returns to stillness. The fault thread remains as a scar of rearranged lattice and altered domains. The ending turns softly toward what follows a quake. The next section moves to how magnetic stresses can load the crust in a patterned way. It follows how field geometry can choose where strain is placed, and why some regions fail earlier than others. A magnetic field can load the crust without touching it, like invisible tension laid across a rigid shell. Magnetic stress twists and pulls the crust because field lines resist being bent. In that region, the primary visual anchor is a pale auroral ring that circles the star as a thin halo of light. The ring is smooth and steady. It is not a flicker. It follows the magnetic geometry rather than the surface texture. A faint gradient in brightness runs across the ring. One edge looks sharper, the other edge fades into dim haze. Light behaves as a soft band that traces where particles and fields guide energy outward. The first payoff arrives early. A quake can be triggered from above as well as from below. The crust is a stiff shell. It still must obey stresses imposed by the magnetic field. The first core concept is magnetic stress. Magnetic stress is force from bent magnetic field lines. Field lines are a useful picture, not physical wires. Yet the field stores energy when distorted. Like a stretched elastic net, it pulls back toward a simpler shape. Like a tensioned rope grid, it transmits force across distance. This matters because stress can be applied in patterns that do not match the crust's internal seams. The second core concept is shear. Shear is sideways distortion without much change in volume. In a crust, shear accumulates along planes and boundaries. In a magnetic field, shear appears when the field is twisted, or when regions with different motion drag lines in different directions. The crust feels that drag as a sideways force. The physical details stay concrete. Along the surface, the ring sits above a zone where the crust is slightly warmer. Warmer material yields sooner. Cooler material holds longer. A subtle temperature gradient becomes a mechanical map. The payoff follows the gradient. Small thermal differences can decide where magnetic stress breaks the crust. One number anchors the scale safely. In magnetar-class objects, magnetic fields can reach about 100 trillion Gauss, like a pressure so intense it could dominate ordinary material forces. The exact value varies. The order of magnitude explains why the crust cannot ignore the field. The scale shift follows. A field shaped by motions deep inside the star can control the surface pattern of stress. It connects unseen interior processes to a visible ring. A checkpoint lingers on the halo. The ring is not uniform. It shows thin arcs and dim gaps. The arcs drift slowly in position as the magnetic configuration evolves. The drift is calm. It can take months or years. Yet stress can still be stored during that calm drift. The payoff arrives in that quiet motion. A slow change in field shape can steadily load a brittle shell even when the surface seems still. The crust has seams and layers. The magnetic stress does not care about the grain direction. It can force shear across domains. That mismatch concentrates strain in places where seams intersect the stress direction. A new visual anchor settles under the halo. A faint network of lines appears on the matte surface. The lines are not glowing. They are subtle changes in scattering. They mark domain boundaries and old fault traces. The halo ring passes overhead like a calm ruler. The payoff follows the overlay. Magnetic patterns can choose where the next break occurs by aligning stress with pre-existing weak lines. The crust yields at the intersection of the two maps. Another checkpoint moves deeper without haste. The magnetic field is anchored partly in the outer layers and partly deeper, depending on conductivity and composition. Conductivity is the ability to carry electric current. Current sustains magnetic fields. The crust is conductive because the electrons move through it. That makes the field evolution slow. It also makes stress persistent. The payoff arrives as a stable explanation. High conductivity means the field can remain twisted for long periods. That allows stress to build without immediate relaxation. Yet this is where a limit of intuition arrives gently. Magnetic fields in dense matter are not observed directly. The halo and timing signals are indirect. Many different field geometries can produce similar surface patterns. Models must assume a distribution of currents and a crust conductivity profile. Those inputs are uncertain in the deepest layers. This is the limit of inference. The field can be mapped only in broad strokes. Fine structure remains hidden. It is also a limit of resolution. Signals smear details across space and time. The crust and field together form a coupled system that cannot be fully disentangled from far away. The narrative returns to a calm mechanical picture. A twisted field applies torque to the crust. The torque is not uniform. It peaks where curvature of field lines is greatest. It also peaks where the crust is thinner or warmer. The halo ring's sharper edge marks a region of stronger field curvature. Under that edge shear, strain rises. The payoff lands with clarity. A quake can be initiated where magnetic curvature is steepest, not where the surface looks most rugged. The first slip can be small. A microscopic displacement along a seam can release enough stress to trigger larger rearrangements. The halo ring can brighten briefly if energy release channels along the field. Brightening is not guaranteed. Yet the coupling provides a route. The crust shifts. The field relaxes slightly. Both adjust together. The primary analogy rests here and remains unique. The crust under magnetic stress is like a thin sheet of rubber coated in dry paint. The rubber can stretch slowly. The paint resists. Fine cracks appear when stretch exceeds the paint's tolerance. The cracks form along weak spots and then connect. This matters because magnetic stress can load the crust gradually while failure occurs abruptly. A final scale shift widens the view. The halo ring traces a surface zone. The source of stress can lie deeper and evolve over long times. A year of slow twist can end in a moment of slip. The ring then settles again. The surface returns to matte stillness with new subtle lines. The next section moves from stress and triggering to how the crust handles heat. It follows the way thermal gradients and conductivity guide where strength changes over time. Heat leaves a neutron star crust in patterns that look calm, yet those patterns decide where the shell becomes brittle or forgiving. Thermal gradients shape crust behavior because temperature changes stiffness and how stress moves. In that region, the primary visual anchor is a slow drifting band of faint glow that wraps the star like a dim latitude line. The band is not bright. It is a gentle warmth trace thinner than the star's curve suggests. One edge is sharper where the temperature drops quickly. The other edge fades where the gradient spreads out. The physical detail is a layered temperature gradient that steepens near the surface and relaxes deeper down. Light behaves as a muted haze over the warmer band, as if the matte surface carries a soft breath of heat. The first payoff arrives early. A crust does not fail only because stress rises. It fails because temperature sets how much strain can be stored before yielding. The first core concept is thermal conductivity. Thermal conductivity is how easily heat flows through material. In the crust, electrons carry much of that heat. They move through the lattice like a dense current of charge, like a copper bar that spreads warmth from one end to the other. A conductive crust smooths temperature differences, like a stone floor that stays cool because heat travels away. A conductive layer prevents hot spots from lingering. This matters because smooth temperature means smoother stress, and fewer places are pushed close to failure. The second core concept is a thermal gradient. A thermal gradient is a change in temperature with depth. In a neutron star, the gradient can be steep near the surface. It can be gentler, deeper down. The steep part creates a thin zone that cools and contracts faster. The physical consequence is a mismatch in shrinkage. The payoff follows directly. Mismatch in shrinkage creates shear stress even without any external twisting. The glow band remains as a quiet checkpoint. Beneath it, layers of the crust cool at different rates. The outermost layer loses heat quickly. The next layer lags. The lag creates tension. The shell is curved, so tension cannot be relieved by simple expansion. It must be distributed along the dome. A second visual anchor appears within the glow band. A narrow crescent of slightly dimmer haze sits beside a brighter strip. The crescent marks a region where conductivity is lower. Lower conductivity can happen when the lattice has more impurities and defects. Defects scatter electron motion. Scattering reduces heat flow. The payoff arrives in the crescent. Where conductivity drops, heat remains localized. Local heat keeps the lattice slightly softer. Softer regions can yield earlier under the same stress. One number anchors time. After formation, a neutron star can cool strongly in its first 1,000 years like an ember, fading to a dull coal over a long night. Cooling continues after that, yet the early phase sets many gradients. The scale shift is gentle. A temperature change that happens over years can alter stresses that release in less than a second. Long cooling history can decide short fracture events. The narrative moves closer to the microscopic carriers. Electrons in a lattice can carry both heat and electric current. Their ability to carry heat depends on how often they scatter. Scattering happens on impurities on lattice vibrations and on boundaries between domains. The crust therefore has a thermal texture. Some regions are like smooth channels, others are like rough passages. The payoff is immediate. Thermal texture creates stress texture because contraction follows temperature. Another checkpoint widens to include the magnetic field without letting it dominate. Magnetic fields can redirect heat flow. They can guide electron motion along certain directions more easily than across them. That creates anisotropic heat transport. The glow band's sharp edge can align with field geometry. The physical detail becomes a boundary line that stays fixed over long times. It marks a place where heat prefers to exit. The payoff follows from fixed boundaries. Persistent thermal boundaries allow persistent stress boundaries. The crust can be loaded repeatedly in the same zones. Now a limit of observation arrives softly and precisely. Temperature maps are inferred from radiation that escapes the surface. That radiation is shaped by the outermost layers and by gravity. Many different internal temperature profiles can produce similar surface emission. It is a limit of resolution. The surface is seen as an integrated signal. Fine-scale thermal patches can be smeared out. It is also a limit of modelling. Thermal conductivity depends on impurity content and on microstructure like pasta layers. Those details are uncertain at depth. As a result, predicted gradients can vary. The glow band is a hint, not a direct measurement of the interior. The story returns to the crust's mechanics in a calm way. When a region is warmer, the lattice is more flexible. Flexibility can be helpful. It can allow stress to relax slowly rather than storing it. When a region is colder, the lattice is more rigid. Rigidity can be risky. It can store more stress before yielding, and then release it abruptly. The payoff is clear. Cooling can make the crust quieter in one sense and more brittle in another. It reduces thermal agitation, yet it sharpens the contrast between zones. Another visual anchor appears near the edge of the glow band. A thin dark line traces a place where the surface scatters light differently. It is not a new fault. It is a boundary in microstructure. It may be a domain boundary zone where impurities concentrate. Such a zone lowers conductivity. Lower conductivity sustains the glow band, the payoff follows. A thermal feature can be self-sustaining because the microstructure that creates it is reinforced by the stresses it generates. The primary analogy rests here and remains unique. The crust under thermal gradients is like a thick candle cooling after being poured. The outer skin hardens first. The interior stays warmer and contracts later. Fine cracks and seams can form where contraction is uneven. The candle can look smooth from afar. It still contains internal tension lines. This matters because a neutron star crust can carry hidden stress from simple cooling. A final scale shift widens the view. The glow band can persist for long spans as cooling and conductivity evolve. Over decades or centuries, small changes in conductivity can move the band. Over a moment, a quake can release stress at the band edge. The next section moves from thermal texture to the deeper motion of free neutrons. It follows how superfluid behavior can lock to the crust and then slip in sudden steps. Beneath the crust, a hidden forward fluid can carry rotation in a way that refuses to behave like ordinary spinning matter. A neutron superfluid in the inner crust can store angular momentum and release it in sudden slips. In that region, the primary visual anchor is a quiet field of invisible threads that become visible only as a faint pattern of aligned dimples in the crust. The dimples are tiny depressions. They sit in long rows. Each row follows a gentle curve that echoes the star's rotation. The physical detail is a sparse lattice of pinning sites where motion is held in place. Light behaves as a soft change in scatter along the rows, as if the matty surface has been combed in one direction. The first payoff arrives early. Sudden changes in spin timing can come from internal slippage without any surface fracture. The first core concept is a neutron superfluid. A neutron superfluid is a frictionless flow of neutrons at low temperature. It is not a river, it is a quantum state. Like honey that suddenly turns into a smooth sheet with no stickiness resistance can vanish. Like a crowd moving in perfect step through a narrow passage flow, can become coherent rather than turbulent. This matters because a superfluid can keep rotating differently from the crust for long periods. The second core concept is a vortex. A vortex is a thin core around which superfluid circulates. Rotation in a superfluid is not spread smoothly. It is carried by many vortices. Each vortex is like a thread of circulation. The thread can be pinned. Pinning means vortices stick to structures in the crust. Like burrs caught on fabric threads can snag on lattice features. Like hooks holding a net in place, pinning sites keep vortices from moving freely. This matters because pinned vortices allow a rotation difference to build between the superfluid and the crust. One number anchors the scale. A single square centimetre can host about 1 million vortices like a field of fine hairs packed on a fingertip. The density changes with rotation rate. The comparison shows the extreme fineness of the pattern. The scale shift follows naturally. Each vortex is microscopic, yet together they decide how an entire star changes its spin. A visual checkpoint steadies on the combed rows of dimples. The rows are not actual holes, they are a surface hint of deep structure. In the inner crust, nuclei and pasta-like shapes provide pinning landscapes. A vortex line prefers to sit where energy is lower. Lower energy often occurs near a nucleus cluster or along a defect. Over time, stress grows in a different currency here. The crust slows slightly because of external braking. The superfluid resists changing its rotation because vortices are pinned. The payoff arrives with calm clarity. A lag builds between two rotating components without visible motion. The lag is stored as a difference in vortex arrangement. When the lag becomes too large, pinning fails in a cascade. The cascade is not a shattering. It is a collective unpinning where many vortices jump to new positions. Another visual anchor appears in the inner layers. A thin band looks darker. It marks a region where pasta geometry changes and pinning strength changes. Along that band, vortices can pile up like threads pressing against a fence. The physical detail is a boundary layer where vortex density becomes higher on one side. The payoff follows. Boundaries in microstructure can act like dams for vortex motion. When the dam breaks, stored rotation can be transferred abruptly to the crust. The crust spins a little faster. Timing jumps. The star returns to a new steady state. Now a limit of intuition arrives softly and precisely. In everyday fluids, friction and viscosity explain how rotation couples between layers. In a superfluid, those concepts fail. Coupling occurs through vortices and through interactions with the crust lattice. Those interactions depend on uncertain microphysics and on the exact structure of pasta and defects. This is a limit of modelling. Direct observation of vortices is impossible. Timing signals offer only integrated evidence. A measured spin jump can be produced by different internal vortex scenarios. This is the limit of inference. The details of where vortices pin and how they unpin remain partly hidden. The narrative returns to calm mechanics. Vortices do not move smoothly when pinned. They creep in small steps or stay fixed. When unpinning begins, motion can spread like a chain reaction. One vortex moves. It changes local flow. That change nudges neighbours. The payoff lands as a small unlock. A sudden spin change can be a collective adjustment rather than a single fracture. It can happen without a visible fault line. Another checkpoint widens the view to the crust as a whole. The crust and the superfluid exchange angular momentum. The exchange is mediated by vortex motion. If vortices move outward, superfluid rotation slows. If they move inward, it speeds. The direction is set by the need to match the crust's changing spin. The physical detail remains in the combed pattern. The rows of dimples suggest a preferred direction in deep pinning structures. That preferred direction can make unpinning more likely in certain regions. The payoff follows. Even without a quake, the star can have preferred zones where timing events originate. The primary analogy rests here and remains unique. The superfluid and crust resemble two stacked skating rinks. The top rink is rough and slows easily. The lower rink is nearly frictionless. Thin pegs connect them. When pegs hold, the lower rink keeps its speed. When pegs release together, speed is transferred suddenly. This matters because timing jumps can be understood as coupling events between a rigid shell and a nearly frictionless interior component. A final scale shift softens the ending. Microscopic vortices form and move on tiny length scales. The consequences can be tracked over years as repeated timing steps. Between steps, the system settles. The combed pattern remains as a faint surface hint of deep order. The next section moves from rotation to chemistry under pressure. It follows how electron capture and related changes reshape the crust as matter is slowly pushed deeper. A crust changes its composition without melting, as if chemistry quietly steps downward under pressure. Electron capture reshapes nuclei in the crust because the squeezed electrons can merge into nuclei and change their charge. In that region, the primary visual anchor is a descending staircase of thin bands, each band a slightly different shade on a curved wall of depth. The bands are layers of composition. Their boundaries are crisp like faint contour lines. Each boundary casts a subtle shadow because lattice spacing shifts across it. Light behaves as a soft change in scatter when one layer gives way to the next. The first payoff arrives early. Composition changes are not a decoration. They alter stiffness and heat flow, which changes where the crust stores stress. The first core concept is electron capture. Electron capture is an electron joining a nucleus and changing a proton. One sentence holds the definition. Two plain images follow. Like a bead sliding from one side of a balance to the other, charge shifts without a visible jump in mass. Like a key turning inside a lock, identity changes, while the structure stays in place. This matters because charge controls how nuclei repel each other and how the lattice is arranged. The second core concept is pressure-driven stratification. Stratification is layering caused by changing conditions with depth. In the crust, pressure rises steadily downward. Rising pressure favours nuclei with lower charge relative to their mass. That preference makes composition change in steps. The physical detail stays tangible. Each step is a boundary where one lattice pattern gives way to another. The boundary is not a gap. It is a zone where defects concentrate because two patterns must meet. Those defects can scatter electrons. They can also concentrate stress. The payoff follows the boundary. A composition change can create a weak seam, even when the crust remains solid everywhere. One number anchors the scale. At depths of about 1 kilometer pressure can be high enough to push many such changes to occur, like stacking the weight of a mountain range onto every square centimeter. The exact depth varies with the star and with composition. The order of magnitude keeps the picture stable. The scale shift follows gently. A process that occurs at the scale of a nucleus can rewrite an entire kilometer-thick shell. In time, that shell circles the star and influences global behavior. A checkpoint lingers on the staircase wall. Each band has a slightly different texture. Some bands look smoother, some look faintly speckled. The speckling reflects impurity content. Impurities are nuclei that do not match the dominant species. They sit like misfit tiles in the floor. Misfit tiles distort their neighborhood. The payoff arrives with the speckling. Even a small impurity fraction can reduce thermal conductivity because electrons scatter more often. That can sustain a temperature gradient. A temperature gradient can then drive stress through uneven contraction. The staircase becomes more than chemistry. It becomes mechanics. Another visual anchor appears along one boundary. A thin, bright line traces the edge where lattice spacing changes. The bright line is subtle. It suggests a slightly different scattering of light and a slightly different stiffness. The payoff follows. A boundary can reflect or guide vibrations in the crust, making some oscillations linger and others fade quickly. This connects composition to ringing modes after a quake. The narrative moves into the slow clock of burial. As time passes, matter in the crust can be pushed deeper by the gradual compression. Each deeper step triggers new captures. The lattice adjusts without melting. The process is quiet. It is like a slow conveyor of identities. The payoff is calm and immediate. A crust can evolve even in apparent stillness because pressure is a persistent sculptor. Now a limit of observation arrives softly and precisely. The composition staircase cannot be seen directly. Signals that escape are shaped by surface layers and by gravity. Cooling curves and oscillation patterns offer indirect clues. Many different composition profiles can fit the same outward cooling behavior if conductivity is adjusted. This is the limit of inference. It is also a limit of modeling. Electron capture rates depend on nuclear structure far from stability. Those properties are uncertain at the extremes found in the crust. Small changes in assumed rates can shift where boundaries appear and how sharp they are. The staircase is a model guided by physics, not a photographed interior. The story returns to physical consequences. Each capture reduces charge. Reduced charge changes electrostatic repulsion. That can change lattice spacing and shear strength. Some layers become slightly more compliant. Some become more rigid. The staircase therefore becomes a map of mechanical contrast. The payoff follows. Mechanical contrast creates preferred slip planes, which can shape how quakes propagate and how oscillations are excited. Another checkpoint focuses on the boundary zone again. Defects cluster there because two lattice arrangements meet. Clusters of defects act like a rough patch in an otherwise smooth road. They slow electron flow, they change heat transport. They also act like stress concentrators. The payoff arrives as a small unlock. A single boundary can be a thermal bottleneck and a mechanical fault guide at the same time. The crust becomes a layered instrument with seams at many depths. The primary analogy rests here and remains unique. The composition staircase resembles a layered cake that is baked in stages. Each layer sets before the next is added. The boundaries are thin and firm. When pressure is applied, sliding prefers the interfaces. This matters because the crust's chemistry creates interfaces that shape how it deforms under load. A final scale shift widens the view. Electron capture changes nuclei one by one. Over long spans, those changes define the thermal and mechanical profile of a whole star. The staircase wall fades into the broader inner crust where free neutrons flow between clusters. The next section moves to oscillations after quakes. It follows how the crust can ring, how waves travel through layers, and what those waves can reveal despite the limits. After a quake, the crust can continue moving without breaking again, as if the shell hums in silence. The crust rings because elastic waves travel through layers and reflect from boundaries. In that region, the primary visual anchor is a set of expanding ripples on a matte sphere, like faint circular bands spreading from a quiet point. The bands are not liquid waves. They are zones of tiny strain that move through the solid. Each band has a crisp leading edge. Behind it, the surface returns to stillness. The physical detail is a sharp wavefront that curves around the star and bends where layers change. Light behaves as a slight shift in scatter along the moving edge, as if microfacets tilt together for a moment and then relax. The first payoff arrives early. A ringing crust can reveal where strong boundaries sit because waves reflect and slow at those depths. The first core concept is an elastic wave. An elastic wave is a moving distortion in a solid. It carries energy without carrying material along. Like a pulse travelling along a taut ribbon, a bend moves while the ribbon stays in place. Like a ripple passing through a pile of dry beads, contact forces pass on motion without the beads flowing away. This matters because information about stiffness can travel through the crust after a disturbance. The second core concept is a mode. A mode is a standing pattern made by waves that reflect. In a curved shell, some patterns fit the circumference neatly. Others do not. Those that fit can persist longer. The payoff follows from fit. A mode can store energy in a stable shape and release it slowly as it damps. One number anchors the scale. Some crust modes can have periods of about 1/10 of a second, like a slow heartbeat in an otherwise silent object. The exact value depends on crust thickness and stiffness. The order of magnitude frames the timing. The scale shift is gentle. A slip that happens in a fraction of a second can set vibrations that persist for many seconds. A local event can excite global motion. A checkpoint lingers on the ripple bands. As the wavefront travels, it meets a boundary where composition changes. The boundary is the staircase layer from deeper chemistry. It is also the transition toward pasta geometry. At each boundary part of the wave reflects. Another part transmits with a changed speed. The physical detail is a slight kink in the band. The kink marks where the wavefront bends. The payoff arrives in that bend. When a wavefront bends, it is a sign that stiffness changes with depth. It is a sign that layers are not uniform. Another visual anchor appears below the surface. A faint internal arc forms where a reflected wave meets an incoming one. The meeting region becomes a standing pattern. The pattern is not visible as a bright light. It is visible as a stable line of enhanced strain. The payoff follows. A standing pattern concentrates stress in repeatable places that can influence where later fractures prefer to occur even if no immediate break follows. The shell learns from its own ringing. The story moves calmly to damping. Waves lose energy through several routes. Energy can scatter on defects and impurities. It can couple to the neutron background. It can leak into the core. The crust is layered, and each layer offers a different path for loss. The payoff is immediate. Damping time is a fingerprint of microstructure. A crust with many impurities damps faster because scattering is stronger. A crust with smoother layers can sustain ringing longer. Now a limit of observation arrives softly and clearly. Ringing is inferred from indirect signals. Those signals can be changes in emitted radiation in some events. They can be timing changes and small modulations. The signals integrate over the whole surface and over time. Fine spatial patterns of modes cannot be resolved. This is a limit of resolution. It is also a limit of inference. Many different mode combinations can reproduce similar observed frequencies. Models must assume a crust thickness, a composition profile, and a magnetic configuration. Those assumptions influence predicted mode spectra. Uncertainty and pasta stiffness can shift predicted frequencies. The ringing is heard through a wall. The wall is thick and the sound is filtered. The narrative returns to the ripple bands with gentle precision. In that region, waves do not travel at one speed everywhere. Near the surface, the lattice is stiffer or softer depending on temperature and composition. Deeper down, free neutrons and pasta geometry change effective shear strength. The wavefront curves as it samples these regions. The payoff arrives as a small unlock. Wave curvature is not random. It is shaped by a layered interior, and it can encode the depth of strong transitions. Another checkpoint focuses on reflection. At the crust core, boundary stiffness changes sharply. Some wave energy reflects strongly. That can create a long-lived standing pattern in the crust. The physical detail is a band that stops expanding and becomes a fixed circle. The circle remains while other ripples fade. The payoff follows. Persistent circle suggests a deep reflector, and deep reflectors suggest major structural boundaries. The circle is a map of interior contrast. The primary analogy rests here and remains unique. The ringing crust resembles a bell made of layered glass. A tap produces tones. Some tones are clear and long, others are quickly muffled. The tones depend on thickness and on hidden seams inside the glass. This matters because the crust's oscillations can act like tones that carry information about thickness and seams even when direct viewing is impossible. A final sail shift widens the perspective. A mode pattern is defined by wave behavior at microscopic shear strength, yet it spans the entire star's circumference. A tiny change in lattice stiffness can shift a global frequency. Over time, repeated quakes can slightly alter the mode spectrum by changing defects and seams. The ripples fade, the matte sphere returns to stillness. The next section moves from transient ringing to long-term evolution. It follows how the crust ages, how defects accumulate, and how the shell's ability to hold strain changes over thousands of years. A crust can appear unchanged for ages, yet its microstructure slowly rewrites how strong and how brittle it becomes. Crust aging is the gradual accumulation and rearrangement of defects under stress and cooling. In that region, the primary visual anchor is a mosaic of matte plates on the surface, each plate separated by hair-thin seams that glint faintly at a low angle. The plates are domains with slightly different crystal orientation. The seams are boundaries where lattices misalign. Along some seams, a faint darkening appears. It is a line where scattering changes because micro-cracks and impurities cluster. The physical detail is a network of seams that forms polygons with corners that concentrate strain. Light behaves as a soft sparkle only at certain angles, revealing which seams are fresh and which are old. The first payoff arrives early. The crust strength is not a single number. It is a living pattern shaped by repeated stresses, cooling and chemical changes. The first core concept is a defect. A defect is an imperfection in a crystal lattice. In ordinary solids, defects include missing atoms and dislocations. Here, defects include misfit nuclei domain boundaries and irregular pasta structures. Like a small knot in wood grain, a defect bends stress lines around it. Like a tiny chip in glass, it becomes a place where cracks can start. This matters because the crust stores stress in the lattice, and defects decide how that stress is released. The second core concept is creep. Creep is slow deformation under constant stress. It is not a sudden slip. It is a gradual rearrangement that can happen even in a solid. Like a glacier that moves without splashing a crust can adjust without obvious fracture. Like a thick wax block that slowly sags under its own weight strain can relax over time. This matters because creep can reduce the buildup of catastrophic stress, yet it can also concentrate damage into certain seams. One number anchors the timescale. Over about 10,000 years, a crust can cool and settle enough that its defect landscape changes noticeably like a stone wall, weathering through many seasons. The exact span varies with temperature and field stress. The order of magnitude frames the slow evolution. The scale shift follows gently. Defect motion at microscopic scales can reshape global quake behavior over millennia. The mosaic plates return as a calm checkpoint. Some plates are larger, some are smaller. At their edges, seams are not straight. They meander slightly. Meandering increases seam length and increases potential slip area. At a corner where several plates meet the surface shows a tiny ridge. The ridge casts a thin shadow. That shadow marks a place where stress concentrates because geometry forces forces to converge. The payoff arrives at the ridge. Corners and junctions act like stress amplifiers, and they become preferred starting points for future failure. Another visual anchor appears deeper. Beneath the mosaic, a thin layer of impurities forms a faint band. The band is the remnant of composition steps from electron capture. It is a chemical seam. It is also a thermal seam because it scatters electrons and reduces heat flow. The physical detail is a boundary that is smoother than a crack yet still distinct. The payoff follows. Chemical seams become mechanical seams because a temperature and stiffness change across them. A crust ages by building more seams, not by becoming uniformly weaker or stronger. Creep provides the quiet motion that makes this possible. Under constant load, dislocations can move. Domain walls can shift. In the pasta region, sheets can slowly relax. These motions do not require a melt. They require time and a path through the defect landscape. The payoff arrives as a simple unlock. Aging can make the crust tougher in some directions by locking structures while making it more fragile along certain planes by sharpening seams. Another checkpoint widens to include the magnetic stress pattern. If the magnetic configuration is stable, it loads the same zones repeatedly. Those zones experience repeated small adjustments. Adjustments can polish certain seams and roughen others. The physical detail is a set of seams that align roughly with the earlier halo geometry visible as a faint preferred orientation in the mosaic. The payoff follows. Repeated loading creates memory. The crust develops preferred pathways for stress release, which can make quakes more predictable in location even if their timing remains uncertain. Now a limit of observation arrives softly and clearly. Aging occurs mostly beneath the surface. Surface emission and timing signals provide only indirect clues. A surface mosaic cannot be imaged in detail. Even if a global modulation is observed, it integrates over vast areas. This is the limit of resolution. It is also a limit of inference. Different defect distributions can produce similar quake statistics and similar damping behavior. Models must assume how defects move under extreme conditions, and that microphysics is uncertain. The crust's aging is therefore a plausible story constrained by signals, not a direct record. The narrative returns to a tangible scene. The mosaic plates seem still, yet at their seams tiny rearrangements occur. A seam can slowly widen as micro-cracks coalesce. Another seam can close as material relaxes and rebinds. The surface ridges shift by tiny amounts. The payoff arrives calmly. Aging is not only damage, it is also healing in a limited sense where stress redistribution can reduce sharp peaks. Another visual anchor appears at a seam that crosses a thermal band. The seam's glint is brighter on the cooler side. Cooler material is more rigid and scatters differently. The physical detail is a contrast line that tracks both temperature and structure. The payoff follows. Temperature history imprints onto the mechanical landscape, and that imprint can persist longer than a single quake cycle. The primary analogy rests here and remains unique. The aging crust resembles a dried riverbed of clay. At first, it cracks in a simple pattern. Over time, repeated drying and slight wetting change the crack network. Some cracks deepen, some heal. The pattern becomes a stable mosaic that still shifts at the edges. This matters because a neutron star crust can develop a lasting seam network that guides future slips. A final scale shift widens the view. The mosaic is made of domains far smaller than the star, yet it wraps a sphere with a circumference measured in tens of kilometers. The slow reshaping of seams over thousands of years can change how the star responds in a single second. The next section moves from aging to the extreme hardness of the crust. It follows what sets the shear strength, how close the crust is to a perfect solid, and why the strongest layers still carry weak seams. The crust's strength is often described as extreme, yet it behaves like a disciplined, brittle solid with precise ways of giving up. Shear strength sets how much sideways stress the crust can hold before it slips. In that region, the primary visual anchor is a smooth matte plane crossed by a single raised ridge that runs for a long distance and then fades. The ridge is not tall. It is a shallow swell like a frozen wave. Along its crest, tiny facets catch light in a narrow line. On one side, the plane looks slightly darker because microtexture scatters light differently. The physical detail is a sharp shear boundary marked by a ridge and a faint shadow, a place where the lattice has shifted by a tiny offset. The first payoff arrives early. Ultra-hard does not mean unbreakable. It means stress can build higher before a controlled slip begins. The first core concept is shear modulus. Shear modulus is resistance to sideways deformation. It describes how stiff a solid is against shape change, like a thick rubber eraser that resists twisting a high shear. Modulus keeps shapes from warping easily. Like a tightly woven fabric that resists being skewed, it pushes back when pulled sideways. This matters because a high shear modulus allows the crust to store more elastic energy for the same small strain. The second core concept is yield. Yield is the point where permanent deformation begins. In a crust, yield can be a sudden slip along a plane. It can also be a local rearrangement around defects. The payoff follows from yield. When yield is delayed, a larger reservoir of energy can accumulate and the release can be sharper once it starts. One number anchors the idea safely. The crust can sustain strains of about 1/10 before breaking into models like bending a ruler far enough that it finally snaps rather than springs back. The precise value depends on impurities and temperature. The order of magnitude captures the message. The scale shift follows gently. A tiny fractional strain at the lattice level can translate into a ridge that runs for kilometers across the surface. A microscopic decision becomes a global feature. A checkpoint lingers on the ridgeline. It is smooth at a distance. Up close, it is composed of many small steps. Each step is a microfault where the lattice shifts by a tiny amount. The steps align to form a coherent plane. That plane is not a clean cut. It is a rough interface with defects that interlock. The payoff arrives in the step pattern. A rough interface can hold strongly until a critical stress, and then slide in a sequence of small jerks that add up to one event. Another visual anchor appears beside the ridge. A narrow band of fine grain texture follows it like a shadow twin. The band is a damage zone. It contains a higher density of defects. It scatters light more diffusely so it looks duller. The physical detail is a gradient in texture that fades away from the ridge. The payoff follows. Damage is not uniform. It is concentrated near shear planes, and that concentration can lower the local yield threshold for the next event. The narrative moves deeper. Shear strength depends on temperature. It depends on defect density. It depends on composition boundaries created by electron capture. It also depends on pasta phases that can behave like layered solids. In some regions, pasta can be stiff. In others, it can shear more easily along planes. The ridge on the surface reflects an average of these interior properties. The payoff arrives as a small unlock. A single surface ridge can encode a history of many layers cooperating, each contributing resistance and then yielding in sequence. Now a limit of intuition and observation arrives softly and precisely. Strength at these conditions is not measured directly. It's inferred from models and from indirect signals like quake energetics and oscillation frequencies. Many parameters are uncertain. Impurity content at depth is not known. The exact arrangement of pasta is not known. This is the limit of modelling. Even if timing events are observed, they do not uniquely identify the strain at failure. This is the limit of inference. A ridge like the one imagined cannot be mapped in detail from far away. Resolution limits smear fine structure. The story returns to the ridge's calm geometry. The crest's shallow swell suggests that slip is not purely planar. It involves a slight uplift, where material is compressed at the edge of motion. On one side, the surface shows a faint compression ripple. On the other, a faint extension trough. The physical detail is a paired ridge and trough like a gentle fold in a stiff sheet. The payoff follows. Even a brittle slip leaves a geometric signature, and geometry reveals the direction of stress. Another checkpoint widens to the concept of maximum strength. A very pure lattice can be extremely strong because defects are rare, yet a perfectly pure lattice is unlikely. Real crust contains impurities and boundaries. Those features reduce maximum strength but can increase toughness by allowing small relaxations. The payoff arrives calmly. A slightly imperfect crust may avoid some catastrophic failures by releasing stress in smaller steps, though it becomes more complex and layered in behavior. The primary analogy rests here and remains unique. The crust's ultra-hard mat behaves like a frozen lake surface in deep winter. The ice can carry heavy load. It still cracks along lines that run far guided by subtle weakness and stress direction. This matters because strength and brittleness coexist, and the most rigid shell can still choose specific paths for release. A final scale shift widens the view. The ridge and its damage band are features on a shell only a few kilometers thick. That shell sits on a star with a radius of tens of kilometers. Over thousands of years, cooling and chemistry change the shell's strength profile. In a moment, stored energy becomes a slip. The next section moves from crust strength to the deepest boundary of the crust. It follows how pasta layers and the transition toward the core influence the largest scale deformations and the quiet long-term settling that leads toward the final calm resolution. Near the crust's deepest boundary, solidity becomes layered and strange, yet it still guides how the whole star settles over time. The crust-core transition is where ordered structures give way to more uniform matter, and the crust's resistance changes shape. In that region, the primary visual anchor is a curved interior horizon, where matte ribbons and sheets gradually blur into a smooth dark expanse. The ribbons are pasta layers. They bend and fold. They keep a preferred direction. The smooth expanse beneath looks almost featureless by comparison. A thin haze of scattered light outlines the boundary. The outline is not a sharp line, it is a gradient band where texture fades. The physical detail is a seam that is thick, not a crack. It is a zone where sheet-like structures tilt and then dissolve into a different state. The first payoff arrives early. The deepest crust matters because it decides whether stress is trapped in the shell or shared with the interior. The first core concept is the crust-core boundary. The crust-core boundary is the transition from structured crust to fluid like core matter. One sentence defines it. Two images follow, like a shoreline where packed pebbles become soft sand. A solid pattern gives way to a surface that reshapes more easily. Like a braided mat that loosens into loose fibers, coherence fades while material remains dense. This matters because the ability to hold shear stress changes strongly across that zone. The second core concept is viscosity. Viscosity is resistance to flow in a fluid. It controls how quickly motion is smoothed out. Like thick honey that flows slowly in a quiet bowl, high viscosity delays rearrangement. Like cold tar that creeps without splashing, it spreads stress over time. This matters because the interior can absorb disturbances and damp them, reducing long-lived ringing in the crust. A checkpoint holds the ribbon horizon in place. The pasta sheets appear like parallel lanes. Their edges cast faint shadows. The shadows shift as the sheets curve. Between sheets, small cavities exist. They are not empty. They are regions of different composition and density. The textures form a directional fabric. The payoff follows the fabric. Directional fabric means stress is easier to release along certain planes than across them. A quake that begins in the crust can slide into this layered zone and then change its character. It becomes less like a sharp snap and more like a controlled glide. Another visual anchor appears as a slow rolling wave in the boundary band. The wave is not a surface ripple. It is a moving region where layers temporarily compress and then relax. The leading edge is smooth. The trailing edge is more diffuse. Light behaves as a gentle brightening along the compressed arc. The payoff arrives with the arc. A boundary band can act like a buffer. It spreads a sudden stress pulse into a longer, quieter motion. One number anchors the scale safely. The boundary zone can extend for about 1 kilometer in thickness, like the depth of a wide canyon wall from rim to shadowed floor. The exact span depends on the star's mass and temperature. The order of magnitude holds the picture steady. The scale shift follows gently. A zone only a kilometre thick can influence motions that wrap an entire sphere with a circumference measured in tens of kilometres. A microscopic arrangement of nuclei can set the fate of global stress. The narrative moves into long-term settling. Over long spans, the crust cools and contracts. The core responds more like a fluid. The boundary mediates between them. If the boundary is stiff, stress remains in the crust and builds. If the boundary is more yielding, stress can leak into the interior through slow flow. The payoff arrives as a simple unlock. The deepest crust decides whether the star's shell ages by storing tension or by slowly sharing it. Another checkpoint returns to the ribbon horizon and notices a subtle tilt. In some regions, pasta sheets align. In others, they twist. Twisting makes junctions. Junctions create knots in the fabric. Knots concentrate strain. The physical detail is a small bright point where several sheets meet. A bright point marks a locally compressed knot. The payoff follows. Knots can act as anchors for stress, keeping a memory of past loading even when surrounding layers relax. Now, a limit of intuition and observation arrives softly and clearly. The deepest boundary cannot be viewed directly. Only indirect signals escape. Cooling behavior constrains heat transport. Timing changes constrain rotation and coupling. Oscillation spectra constrain elastic properties. Yet many internal profiles can produce similar outward behavior if parameters are adjusted. This is the limit of inference. It is also the limit of modelling. Pasta geometry is sensitive to nuclear interactions at extreme density. Those interactions are uncertain. Small differences in assumed stiffness change the predicted coupling between crust and core. The boundary is therefore a structured hypothesis, not a measured landscape. The story returns to an image that remains calm. In that region, motion is slow. A stress pattern presses down. The pasta fabric yields slightly. The fabric does not tear everywhere. It rearranges at weak junctions. The rearrangement is not dramatic. It is a gradual slip along planes. The payoff arrives as another unlock. Slow rearrangement can erase sharp stress peaks and reduce the chance of repeated brittle failures in the same place. Another visual anchor follows the gradual slip. A faint band of altered texture trails behind the slipping zone. The band is smoother. It scatters less. It is as if layers have been combed into a more ordered alignment. The physical detail is a polished strip in the fabric. The payoff follows. Polished strips can change future behavior by making sliding easier along the same path, creating a long-lived channel for stress release. The narrative widens to time. A crust can endure thousands of years of gradual adjustment between quakes. In those spans, the boundary does steady work. It transfers angular changes. It transfers heat. It transfers stress. The payoff arrives calmly. The star's apparent stillness is supported by continuous internal housekeeping at the deepest seam. The primary analogy rests here and remains unique. The crust-core boundary resembles a layered cliff where hard rock strata meet a deep bed of saturated silt. The cliff can hold sharp edges. The silt can deform slowly. The interface can either support the cliff or allow it to slump in measured ways. This matters because the deepest crust can either preserve sharp elastic behavior or turn it into quiet flow. A final scale shift eases toward a broader perspective. The pasta ribbons and the smooth expanse beneath occupy a thin region relative to the star's radius. Yet that region decides how energy and stress migrate across the whole object. As long-term settling continues, the shell becomes less eager to snap and more inclined to relax. The next section moves into a gentle resolution. It follows how all these layers from surface to boundary settle into a stable rhythm where change becomes softer and slower. The deepest layers do not end with a final snap. They end with a slow settling that turns sharp stress into quiet shape. The calm takeaway is simple. The crust holds memories in its texture, yet time and heat soften those memories into stability. At this distance, the primary visual anchor is a matte hemisphere with a faint belt of dim glow. The belt is not bright. It is a thin, misty ring of light that hugs one latitude. It fades at the edges. The surface beneath remains dark and smooth. A long hairline arc crosses the plane. It is a shallow scar from an old slip. Along the arc, the microtexture changes. It scatters light more evenly, so the arc looks like a brushed stripe on stone. The physical detail is a boundary that is visible as a change in sheen. The first payoff arrives in that sheen. A crust remembers stress through tiny defects, and those defects can be read as texture rather than motion. The first core concept is thermal diffusion. Thermal diffusion is the heat spreading from hot to cold. It is the quiet process that smooths temperature differences. Like warmth moving through a thick slab of rock, it travels slowly and leaves no sharp edges. Like frost melting from the sunlit side of a dune, it reduces contrast and softens gradients. This matters because temperature sets how easily defects move and how quickly stored strain is released. A second payoff follows. When the crust cools, stiffness increases. When it warms, slightly small rearrangements become possible without a quake. The belt of dim glow suggests a mild temperature pattern. It is not a furnace. It is a gentler symmetry. Another visual anchor appears nearby. A cluster of faint patches sits off the belt. Each patch is slightly different in brightness. The edges are soft. The centers are smoother. The patches are not spots of paint. They are regions where the surface has been rearranged and then refrozen. The payoff arrives with the patches. Surface texture can be a map of where internal heating once occurred even after motion has ended. The narrative moves inward through a checkpoint. Beneath the brushed arc, the crust is layered. The upper lattice holds cracks and sit planes. Deeper down, pasta sheets bend and align. Below that, the transition zone blurs structure into a more uniform interior. Those layers do not act in isolation. They exchange stress through contact and through slow adjustment. The second core concept is creep. Creep is slow, permanent deformation under steady stress. It is not a sudden break. It is a gradual drift in the arrangement of matter. Like a glacier moving without breaking into spray, it flows by tiny shifts inside. Like a wax ridge slowly slumping on a warm day, it changes shape without a sharp sound. This matters because creep allows stress to drain away between quakes, reducing the need for repeated brittle failure. The next payoff arrives in the timing. A crust can store energy quickly in a sudden event and then release a portion slowly through creep and heat flow. The main number anchors that idea safely. The outer solid shell is about 1 kilometer thick in many stars, like the depth of a Grand Canyon wall, from rim to shadowed floor. That thickness is small compared with the whole object. It is still large enough to hold layered history. The scale shift follows gently. A kilometer-scale shell contains microstructure on scales smaller than a grain of dust. Those scales connect. Tiny defects shape kilometer-long scars. Kilometer-long scars shape global stress pathways. Another visual anchor holds the calm. Along the brushed arc, the surface shows a subtle paired ridge and trough. The ridge is a low swell. The trough is a shallow dip beside it. The pair marks where material compressed on one side and stretched on the other. Light behaves as a thin highlight on the ridge and a muted shadow in the trough. The payoff that arrives in that geometry, even without motion, shape preserves the direction of past stress and shape persists longer than heat. The story widens to long time. As the interior cools over thousands to millions of years, thermal diffusion continues to smooth gradients. As creep continues, the sharpest stress concentrations relax. This does not erase the crust. It changes how energy is stored. The third core concept is relaxation time. Relaxation time is how long a disturbance takes to fade. It depends on stiffness, temperature, and defect mobility. Like ripples fading on thick mud instead of clear water, motion loses its sharpness faster when internal friction is higher. Like a bell that sounds duller when wrapped in cloth ringing, becomes brief when energy leaks into many small channels. This matters because the crust's future becomes quieter when relaxation time shortens for shear stresses. Another payoff follows. The most dramatic quakes may occur when the crust is young or when changes are rapid. Later, the same physics remains, but it plays at lower volume through smoother pathways. Now a limit of intuition and observation arrives softly and clearly. The interior cannot be inspected directly. Only indirect signals escape. Small changes in rotation and occasional bursts of energy offer hints. Yet many interior arrangements can produce similar outward behavior. This is the limit of inference. It is also the limit of resolution. Fine-scale texture on a distant surface cannot be mapped in detail. A belt of glow can be detected as a broad feature, but the exact structure beneath it is not uniquely determined. The crust story is therefore reconstructed from models not measured layer by layer. The calm payoff arrives even within that uncertainty. Uncertainty does not erase the main arc. A stiff shell stores stress. A layered base modifies how stress moves. Heat and creep decide how the shell settles afterward. Another visual anchor returns to the boundary region in imagination. Deep down, pasta sheets lie like stacked ribbons in a slow current. Their edges are not sharp. They blend at junctions. The blend is a soft seam. The seam is where shear becomes distributed instead of focused. The payoff arrives in the seam. A distributed seam turns a single brittle break into many tiny adjustments. It spreads strain so that the crust's future events become less concentrated. The narrative now eases outward again. The matte hemisphere looks still. The faint belt remains. The brushed arc remains. No new feature appears. The calm rests in repetition and stability. The scale shift becomes a soft closing gesture. In a fraction of a second, a quake can rearrange a fault plane. Over years, creep can smooth the edges of that rearrangement. Over far longer spans, cooling and diffusion can flatten temperature contrast that once guided stress. The closing analogy remains unique and gentle. The crust's long settling resembles a sand dune after wind has stopped. Sharp ripples remain at first. Then grains shift imperceptibly. Edges soften. The dune keeps its form while its smallest features relax into smoothness. This matters because the neutron star crust holds extreme structure without needing constant drama. It becomes a quiet archive of forces and their release. The final transition is a soft landing. The journey through nuclear pasta, starquakes and ultra-hard matte ends at a steady stillness. The next moment contains no new question. It contains only the continuing calm of a dense shell finding balance.